Right, so we're going to continue looking chapter 4, which this section's on rational functions and how we graph them. So we're going to look at asymptotes. We'll check calculator using the table to help us out. But these graphs, they're not too bad to do. And a lot of them look very similar. We just have to learn where we can have holes and where we can have asymptotes. That's very important when we're sketching. Right, so remember, we've talked about this before. If the numerator and denominator have a common factor, then what might happen is you get a hole in the graph, right? Or you get a part that's not connected, but you can't see it on the screen. All right? So let's graph this. Okay, before I even graph it, what value would make the denominator 0? 1. Now, am I going to get a vertical asymptote at 1?
Yes.
Okay, no. Why not?
Maybe I'll add 1 to the entire fraction equation.
So we're not going to get a vertical asymptote, but it's because
They share a common factor.
we have a common factor. Okay, x minus 1 is in the top and the bottom. Okay, so let's just graph it and see what happens. Okay, so we got x minus 1 divided by x minus 1. Okay, so we're dividing two things that are the same. What do you get when you divide two things that are the same? 1, right? So basically, what it looks like is a horizontal line at 1, but it's not connected. That line is actually broken into two pieces. Right? And the only way we could check that is looking at the original problem and realizing if you plug 1 in for x, you divide by 0. All right, so we try to plug 1 in for x, and we don't get anything for y. Go to your table. Same idea. Okay, any question on that one? All right, so we have a hole there, but you can't see it. All right, let's try this one. What value would make the denominator 0 here? 1 again. And if we were to simplify that, we have two things with the same base. What do you do with the exponents when you divide? You subtract them. So this is like graphing x minus 1 to the first power. They're like y equals x minus 1. So it's going to look like a line with a slope of 1 and a y-intercept of negative 1. All right, let's type that in. Okay, x minus 1 squared divided by x minus 1. Okay, so it looks like a line, as I said, slope of 1, y-intercept at negative 1. But what's actually happening at positive 1? There's no y value because we have a hole in the graph. Okay. You can go very, very close to it. 0.999, we get a value. Okay. You go 1.00001, and you get a value. It's just exactly at 1. So it's like it's an infinitely small hole. Okay, just to the left and just to the right, it's perfect. But just at 1, we have what's called a removable discontinuity. Right? Not a vertical asymptote. Yes?
I thought on these calculators it was able to make the hole in the line.
No. We can sketch it. So like if we were going to sketch something that had a hole in it, I would say sketch it like this on paper. Kind of exaggerate it so I can see that there's a hole. But yeah, the calculator can't show us that hole. And that's called a removable discontinuity. Any questions on that?
So it's whatever makes the denominator 0?
Whatever makes the denominator 0.
If that's where your hole's going to be?
And you have a common factor in the top. That's where your hole's going to be. Yep. So if I change this problem to, let's just change one of the numbers. Change plus 1 or minus 1 to plus 1. You know what? Let's even make it plus 3. Now we don't have a common factor. Okay? The top and bottom don't have common factors, so something's still going to happen at positive 1, but it's not a whole anymore. Okay, we're getting a vertical asymptote, right? And it's actually going off the screen. Not sure how high up it goes, but let's see if we can see it. There it is. Getting a vertical asymptote at 1. Just by changing one number from plus 1 to plus 3.
So is it basically if you find a number that makes the bottom 0 and it also makes the top 0 when you plug it in, then it's your whole?
Yeah. Yeah, I guess that would happen because if you had a common factor, it made both the top and bottom 0.
Okay.
Yeah.
Is that like a universal rule that if the problem equals 0 when you plug in the number, it's
The top and the bottom, yeah.
okay.
Yep. Yep, that's a good point. All right, so this represents just a general rational function. You could think of it as like 3x squared plus 2x plus 6 in the top, and 5x squared minus 8x plus 7 in the bottom. Okay, just a rational function. Usually we write it in descending order, and we put the constant at the very end. Okay, this highest degree term is what we call the EBM. Does anybody remember what that stands for? Did that back in chapter 3. Yeah, end behavior model. Okay, the highest degree term in the top, term with the highest exponent, that's called the end behavior model. Well, in the bottom, we also have an end behavior model. That's the highest degree term in the bottom. So if we want to know the end behavior model for the entire fraction, take the end behavior model for the top, take the end behavior model for the bottom, and just divide them. And that's it. That's your end behavior model for the entire fraction. Highest degree term in the top divided by the highest degree term in the bottom. All the other terms don't even matter. They might cause little twists and turns and things like that, but if we just want to know what's this function going to look like if we zoomed way out, like negative 1,000,000 to 1,000,000, that right there describes what it's going to look like. Okay, we don't care about the little twists and turns from the other terms. All right, so think of the end behavior model, big picture idea. Okay, it's the big picture. Right, now, Jamie mentioned this idea earlier. If you have two things with the same base, what do you do with those exponents? Yep.
Oh, cancel?
They cancel if they're the same, but in general, yeah, you subtract them. All right, so we subtract them. Now, what happens if we subtract them? Let's say we ended up with something like that. What happens when your exponent is negative? That negative means it's going to go somewhere. Yeah, it goes down. Okay, if you end up with something that has a negative exponent, all you do is put it in the bottom of a fraction, and it becomes positive. So what do you think that would be if we ended up with that?
1 over x squared.
1 over x squared. So anytime you get a negative exponent, just put it in the bottom of the fraction. And it becomes positive. Okay, so that's our end behavior model for a rational function. Right, and what the end behavior model really does is it gives us a way to find horizontal asymptotes. Because the end behavior model predicts what's going to happen as x gets really, really big. And that's exactly what horizontal asymptotes are. What happens to y as x gets really, really big. So let's start with our EBM. Okay, when I write EBM, it means end behavior model. Okay, Cheryl, what's the highest degree term in the top? 2x squared. We don't care about that minus 1. Minusing 1 doesn't even make a difference. Okay, not if x is a million. Okay, what's the difference? It's so small. Okay, and then in the bottom, Cameron, what's my highest degree term in the bottom?
3x cubed.
3x cubed. All right, so when we simplify it, we've got 2/3 x, and my exponents are 2 minus 3. Okay, I'm going to do 2 minus 3. So what does that give me? 2/3 x to the negative 1.
So that would be 3/2.
And what does that mean? What do I do with that, with this part right here? Just put it in the bottom. Yep.
So you make 2/3 times 1 over x?
Yeah, you could write it as 2/3 times 1 over x, which is exactly what that is. Yep.
Now say if it was like x to the negative second power, it would probably 2 over 3x squared.
Yep, if it was something like this, you would put 2 over 3x squared. Yep. Just take that x term, throw it in the bottom if it's negative. Okay, so that's it. That's your end behavior model. 2 over 3x. And now we use that to find the horizontal asymptotes. Let x get really, really big and figure out what this fraction gets closer and closer to. All right? So start with your denominator. If you let x get bigger and bigger and bigger, what happens to this denominator? Yeah, it gets huge. Okay, if x is a million, triple it, you got 3 million. Then if you take 2 divided by 3 million, what kind of number is that? Very small. In fact, it's approaching 0. So your horizontal asymptote is what letter? Y equals 0. Right, so you just let x get really, really big, and that tells you your horizontal asymptote. You could do really big as a positive number or a really big negative number. It's the same answer. Okay, question on the EBM or horizontal asymptote?
How would it be closer to 0 though for the horizontal asymptote?
Close to the horizontal? Why is it getting closer to 0?
Yeah.
Well, just take a really big number for x, like,
So I put like 2 divided by 3 times like 1 million.
yeah, so we got 2 divided by 3 times, what'd you say, 1 million?
Yeah.
Right, so that's 0.0000006. That's scientific notation. All right, that's anytime you get a negative exponent from scientific notation, that means you move it to the left 7 times and put all the zeros in. All right, so it's very, very close to 0. In fact, I think if you type a number in like this and then hit enter, I put too many zeros, but it automatically changes it to scientific notation. So everybody see why a number with a e to the negative 9 is a very, very small number? Okay. I had too many zeros, but that's okay. All right, let's try this one. Okay, Pat, what's my highest degree term in the top?
2x to the 4th.
Yep. And Derek, highest degree term in the bottom?
3x to the 4th.
Right, so Tyler, what happens when I divide x to the 4th by x to the 4th?
It just becomes 1.
Yeah, these just cancel out. You get x to the 0 power. If you did 4 minus 4, x to the 0 is 1. So what am I left with for my end behavior model? I'm left with 2/3. Okay, now our horizontal asymptote. Okay. In our end behavior model, you let x get bigger and bigger. Well, there isn't even an x here. So as x gets bigger and bigger, what happens to this fraction? Nope, it doesn't get smaller because there's no x there. It's just 2/3. It just stays 2/3 all the time. Right, so if your end behavior model comes out to a number, that's the asymptote. There's no x. Any questions on that? All right. Okay, so last thing we'll do is a couple sketches. Okay, I'm going to write out some different suggestions on how to do the sketches. The most helpful thing is to find the asymptotes. Okay, if you can find those, you're pretty good. Okay, and all the problems we sketched today is what's going to happen is the degree of the numerator will be less than or equal to the degree of the denominator. Okay, when that doesn't happen, the graphs can do some weird things. Okay, but as long as the degree of the numerator is less than or equal to the degree of the denominator, things are usually pretty straightforward to graph. All right, so one thing that might be helpful is to find the intercepts. Find where this graph crosses the x and the y-axis. Right, so to find your x-intercept, plug in 0 for y. To find your y-intercept, plug in 0 for x. Not every graph has x and y-intercepts. Some graphs don't cross the axes. Think of a parabola that's shifted up, like this. We're not sketching parabolas, but this is just an example of a graph that never crosses the x-axis. Okay, same thing with our sketches. They might not always cross. Okay, next thing you want to find is your vertical asymptotes. That's the numbers you plug in that make the denominator 0. Okay, third thing, you're going to find the end behavior model and use that to get your horizontal asymptotes. The next thing we're going to do, we're going to use our table. Okay, so for step 4, use table on calculator. We're going to check the behavior very, very close to the asymptote. So let's say we had a vertical asymptote at 2, or we thought there was one at 2. We're going to check the behavior on each side of 2, very, very close to 2, okay? Like 2.001. And then we're going to check on the other side, like 1.99. Okay? Just like I did when we had that hole when we graphed it. Check the behavior on each side. Okay, and then the last step, we can graph it on the calculator and make sure that what we're sketching matches what we should get. Okay, but I will ask you to find these things as you graph it. I'll ask you for the end behavior model, vertical asymptotes, horizontal asymptotes, and possibly the intercepts, if they exist. Okay, does everybody have the 5 steps?
Not yet.
Oh, yeah? So we had step, everybody have up to step 2? You said that, okay. All right, so first one we're going to try to sketch is f of x equals x minus 1 over x squared minus 6. What's the highest degree term in the top? What is the degree? Yeah, it's not written here, but if you want to put the exponent of 1, you can. Usually we don't. What's the highest degree term in the bottom? 2. X squared, yeah. All right. So I said to you the degree of the numerator will be less than or equal to the denominator, and that happens here. Top is 1, bottom is 2. All right, so let's start with, let's find our asymptotes first. So let's start with the vertical asymptotes. Yep, step 5 is just to use your calculator. Just double check it on the calculator. All right, how do you find the vertical asymptotes? All right, factor. What are you going to factor here? The bottom. Yep. Find the zeros of the denominator. All right, so you're going to take x squared minus x minus 6, set it equal to 0. Okay, we'll have x and x. And I need two numbers that multiply to give me 3 and subtract to give me 1. Yeah, 3 and 2. And what are my signs going to be? -3. Let's check it. X times 2 is 2x. X times -3 is -3x. Perfect. All right, so what are my two vertical asymptotes here?
3 and x is -2.
3 and -2. So before I go any further, I'm going to put those on my graph. Okay, when we draw an asymptote, what kind of line did I suggest to use? Yeah, just make a dotted line. All right, 1 at 3, 1 at -2. Okay, horizontal asymptotes. Okay, to do that, I'm going to find my end behavior model. Andrea, what's my highest degree term in the top? I'm sorry, Adriana. Sorry.
1?
Yeah.
Everyone? No, 1.
Well, the degree of it is 1, but what's actually the term?
Oh,
X,
x.
yeah. Yeah, X. And Paige, what's the highest degree term in the bottom?
X squared.
X squared. So think of that as x to the first divided by x squared. Dalton, can you tell me what my end behavior model will be?
Would it be -x?
Well, let's see. We've got a positive over a positive. So the final answer is positive. Might be a negative exponent, but
So 1 to the, would be x to the -1st?
yeah, x to the -1st, which turns into
1 over x.
1 over x. So there's my end behavior model. Right, so what does that fraction approach as x gets really big? 0. There's your horizontal asymptote. Okay, what the asymptotes do is they break up the grid into sections. Okay, a lot of times when we sketch it, we usually use 3 sections of the graph. Okay, 3 on the top, 3 on the bottom. Okay, we'll see which 3 sections we use this time. Not always, but a lot of time we do. All right, what else? We've got vertical asymptotes. We've got end behavior and horizontal. We'll do step 4 on the calculator in a minute. So let's find the intercepts. Okay, the x-intercept is when you plug 0 in for y. So basically we're asking how we'd make this fraction 0. How would we make it equal 0? What's the only way a fraction can equal 0?
Divide by itself.
And then 0 in the denominator.
0, not in the denominator, in the numerator. Okay, if you have 0 in the top of a fraction, that makes the fraction 0. So what's in the numerator here? X minus 1. Set the numerator equal to 0. That's your x-intercept. So that's where it crosses the x-axis. That's a point on our graph. Okay, and lastly, let's find our y-intercept. Okay, to find the y-intercept, that's where I plug in what number for x? 0. Okay, what's 0 minus 1? -1. 0 squared? Minus 0? Minus 6. -6. All right, so the y-intercept is at 1/6. So maybe about like that. All right, so that's that step. Now I'm going to use my table on the calculator. Okay, so if you haven't typed it in, now we need to type it in. All right, so we got x minus 1 divided by x squared minus x minus 6. All right, where was one of our vertical asymptotes?
3.
3? All right, so we're going to check in our table what happens when we plug in numbers very close to 3, just a little bit above it and a little bit below it. Somebody give me a number that's just a little bit lower than 3.
2.9.
Yeah, 2.99, perfect. Okay. We plug in a number very close to 3, we're down at negative infinity. Okay. So at 2.99, I want you to put a dot way down at negative 40. All right, so basically, way down.
Wait, negative.
Yeah, I can't go to negative 40.
What did you do?
Oh,
for the
negative 40. I
y-intercept?
said negative 4.
Yeah, negative 39.8.
What did you do for the y-intercept?
The y-intercept, just plug in 0 for x.
So, and we have this on test.
What's it? Just plug in 0 for x. And then you get 0 minus 1, and then 0 minus 0 minus 6.
So, like, since it's not on the graph, we just put it as down as we can.
Yeah, it's just going to curve, and it's just going to drop almost straight down.
Okay.
Yeah. Okay. Now I want to see what happens just on the other side. Okay, so what's a number just a little bigger than 3?
2.99.
We did 2.99. Yeah.
3.0001.
Yeah, 3.0001, that's fine. Okay. And now when you plug in a number just a little bigger than 3, you're way up. Okay, so just put a dot as high as you can. Way up. All right, and now do the same thing with the other vertical asymptote. All right, that one's at negative 2. Okay, what's a number that's really, really close to negative 2? Yep, negative 1.99, that's a good one. So when we're at negative 1.99, put a dot as high as you can. All right, and one other number to check. Negative, yeah, that's close enough. All right, so now when we're at negative 2.0001, put a dot as low as you can. All right, and those dots give us a pretty good idea of what it's going to look like. Okay, as we sketch it, we can't cross these dotted lines. All right, we're kind of trapped by them. All right, so this part is going to curve, getting closer and closer. But as I keep going, it has to start getting closer and closer to this line. So it's got to curve at some point and do something like this. Okay, it's got to get closer and closer to each line as we go out. Same thing has to happen in the bottom. As it drops down, it's got to get closer and closer to that line. As it heads to the left, it's got to get closer and closer to that line. So at some point, it has to curve. Now the middle section, it's got to go through all these dots, and it has to be a nice curve, getting closer and closer to the vertical asymptote on the right as you go down, and getting closer to the vertical asymptote on the left as you go up. So that section is going to look something like that. And that's a pretty common picture for these kinds of graphs. It's usually in 3 sections with that kind of S shape in the middle. Let's check the picture. If you didn't put it on Zoom 6, it'll look a little better. Right, so there's our left section. There's that center section, and then the one on the right. And that looks basically what we have. I think theirs turns a little sharper than mine did. I think I made my curve a little bit more gradual. That's fine. If you have what I have sketched there, that's perfect. curve doesn't have to be doesn't have to turn exactly at the right
So
time.
you basically just plug in numbers that are basically close to the vertical asymptote?
Yeah.
Is that what you did?
That's what you do every time. Yep. All right, so we'll try. Let's try one more together, and then I'll have you guys try one on your own. Okay, this time I kind of put down everything you need to find to guide you along. Vertical asymptote, horizontal asymptote, x-intercept, y-intercept. Okay, Nick, how do I find my vertical asymptotes? Okay, look back in your notes at those five steps. I think it's the second or third step. So step 2. So Nick, just look up here. Find those vertical asymptotes. What do I have to do?
Zeros of the denominator.
Yeah, set the denominator equal to 0. All right, so this time my denominator is 2x squared minus 5x. Okay, we're going to factor it, but we don't have to use any kind of complicated factoring here. We just factor out what they both have in common, which is what? X. Take that out. And what am I left with?
2x minus 5.
Yep. Okay. If I wanted to plug in a number to make this first factor 0, what would I plug in?
0.
Yeah, just 0. And if I wanted to plug in a number to make the second factor 0,
5/2.
plus 5 divided by 2. Okay, just for the purpose of graphing, I'm going to write that as a decimal. 5 divided by 2 is 2.5. Okay, so those are my vertical asymptotes. Right, so we'll start with that. 0, 2.5. That's good enough. All right, horizontal asymptotes. Okay, what do I use, the 3-letter abbreviation, to find the horizontal asymptote? Yep, EBM. Jamie, can you tell me highest degree term in the top?
3x squared.
Bottom?
2x squared.
And my, what's it going to come out to when I reduce it?
You're going to need 3 over 2.
Yeah. The same term in the top and bottom. And behavior model is 3 over 2. What happens if you let x get really big in that fraction? It just stays 3 over 2. Or if you're looking for the decimal, it's 1 and 1.5. Okay, so put a horizontal line in at 1.5. Okay, so we get that same basic shape again. We're going to have probably a graph in 3 sections. Usually we get a curve in the middle, and then kind of an L shape on the left and the right of it. Not always, but a lot of times. All right, x-intercept. Okay, that's when you let y equal 0. Okay, the only way you can make this fraction 0 is if the top is 0. All right, so set the top equal to 0. 3x squared plus x minus 4. Okay, now I'm going to hope that we can factor that. Otherwise, we'd have to use quadratic formula, but I think it factors. We've got to put 3x and x. Okay, and 2 numbers that multiply to give me 4. You could do 2 and 2, or, yeah, let's try 1 and 4. Let's do something with that, because I'm thinking 3 times 1 is 3, 4 times 1 is 4, and if I subtract 4 minus 3, I can get a 1. So where would I put my signs? A negative 4 and a positive 1. Let's check. 3x, take away 4x, oh, that's negative 1. So what do I got to do? Just switch my signs. So now we get negative 3 plus 4. Yep, we're good. What would be my first y-intercept? X equals? Yep, negative 4 over 3, which is about negative 1.3 repeating. Okay, and my second y-intercept? Positive 1. So this one crosses the y-axis twice. Okay. Negative 1.3. It's going to cross in that section. I'm guessing we're going to have an L shape, like that. And it's going to cross at x equals 1. Okay, that's going to be a separate part of the graph. Okay, and the last thing we'll find is the y-intercept. All right, page, what's 0 squared?
0.
Times 3?
0.
Plus 0?
0.
And then minus 4. All right. Negative 4. And let's plug 0 into the bottom. Matt, that's how you find your y-intercept. Yep, to find your y-intercept, let x equal 0. All right, now plug 0 in for x in the bottom. Matt, what's 0 squared?
0.
Times 2?
0.
What's 5 times 0?
0.
So what's 0 minus 0?
0.
0, good. So what's my y-intercept? No, not negative 4. Not 0. Yeah, it's undefined. Okay, what that means is this graph that never crosses the y-axis. Okay, it'll never cross it. Okay, you can't divide by 0. All right, so let me type it in so that I can check a point on each side. My guess is I'm going to be down here and then up there. But let's see what happens. All right, so we got 3x squared plus x minus 4. 3x squared plus x minus 4. Divided by 2x squared minus 5x. So I'm going to try a number just to the left of 0. I'm going to try like negative 0.001. And my guess is it's going to be down very low. Anybody already check it? It is? Yeah, negative 800. Okay, so we're down here. So now my guess is if you try a number on the other side, it's going to be way up high. Okay, try 0.001. Yep, positive 800. Okay, now on this other one, this curve in the middle has to stay trapped inside here. And I don't think it's going to take a U-turn and start going back up. I think it's going to continue down. So if we try, let's see, what's that, 2.5? So let's try 2.49. Let's go very close to it. Yep, negative 300. Okay, so we're down very low. And on the other side, it's going to be up very high. Okay, just after 2.5, try 2.51. Positive 300. Right, now draw the shape. Okay, so it's going to curve down Get closer and closer there. Okay, in this section, it's going to come up. It's going to go through that point. Get closer and closer on that side. And then just connect the dots in the middle. Just make it a kind of a smooth curve. Okay, so that's what our sketch should look like. Let's take a look. Okay, notice on the calculator, it had a little trouble sketching this section in the middle because it goes so steep. It can't. The calculator can't sketch things that start to get too steep. So this should actually continue down, and this should continue up. But yeah, that looks pretty good. Okay, so any question on that? All right, I think that's pretty good. Okay, the last one would come out very similar to the other two. Okay, does anybody feel like we need to do one more?
I mean, I'll be agree with this.
But you know what, I'll put the homework up, and those that want to do one more, you can do it. I'll come around and help you. Those that want to start the homework, you got a little over 10 minutes. So the homework, it's page 234. Okay, 1 through 5, just the odds. 9 through 11. 15. 17 to 22. 23 to 25, and 29 and 33. Okay, these are not all graphing. Some of them, you just have to write an asymptote or an end behavior model, but there are some to graph. So if you'd like graph paper, I'll print some out, and I'll put a pile on the table. I'll have it after 10:30 today.